All right, we're looking at number 6 in our thermo review. Number 6 looks an awful lot like a calorimetry problem, almost exactly what we did as a demo in class. They're using aluminum metal, dropping it into a calorimeter with water in it, and seeing what happens to the heat. And right away we can see that the heat is causing the temperature to go up, so we know that the block is giving off heat, which makes sense. So part A says, given that the specific heat of water is 4.18, which we know it is, and the density of water is 1, calculate the heat gained by the water. So you remember the way we tackle calorimetry is we divide it up between the system, which is aluminum, and the surroundings, which is water, and we see how much heat the water gained first. So we set up our calorimetry equation, and we use the specific heat of water. We assume that there are 25 grams of water because they said the density was 1. And then we do final temperature minus initial temperature, and we get a heat of 376.2 joules that was absorbed by the water. So this is the answer to part A. Part B, they ask us to calculate the specific heat of aluminum. So that's sort of the natural next step. You remember that we assume that this heat came from the aluminum, so our heat is going to be negative 376.2 joules. And then we just need the specific heat and the mass and the change in temperature of the aluminum. We are calculating the specific heat. We used 5.86 grams of aluminum, and the aluminum ended at the same temperature. Its final temperature was 26.8, but it started at 109.1, so final minus initial, which gives us a negative number here, which is great, because when we divide both sides by these two, it'll get rid of that negative, and I got 1.28 joules per gram Celsius. By the way, you do need a unit here, so if you're having troubles remembering what it is for specific heat, you can always go up here and cheat a little bit, or you can follow your units through really well if you remember to put them on your numbers. Let's look at part C. In part C, this has got to be the world's dumbest question. They want us to calculate the enthalpy of reaction for the cooling of aluminum in water. The problem is, putting aluminum in water does not cause a reaction. What the heck they're talking about here, I have no idea. I'm pretty sure what they want for the answer, but this is completely idiotic. Any case, you can tell they want the amount of heat in kilojoules per mole of aluminum. So if we have 376.2 joules of heat that was transferred in our previous steps, I think all they want us to do is convert this to kilojoules and then divide by the number of moles of aluminum. So here we go. I've converted my joules to kilojoules, and then I converted the 5.86 grams of aluminum to moles of aluminum. And then all I have to do is do my kilojoules divided by moles to get the amount of heat that they're talking about. I wrote delta H here because they said enthalpy of reaction. It pains me to do this. There's no reaction going on here. That's why I think that this is not a very good question and not very AP-like. But I think that that's what they're going to want. In part D, they want us to calculate the percent error. Shouldn't be too bad. They tell us that the accepted value is 0.9, and we know that we calculated in part B that the specific heat of aluminum was 1.28. So it looks like we were not very close. So let's calculate the percent error. So remember that we do our measured value minus the known value divided by the known value times 100, and I get 42.2%. That's a lot of error. Finally, to part E. Suggest 2 potential sources of error that would lead to a student's experimental value to be different from the actual value. Be specific in your reasoning and make sure any identified error can be quantitatively tied to the student's results. So this is something we've practiced a lot in lab, and I think what they mean by that it can be quantitatively tied to the student's results, they're saying that, remember, we got a specific heat of 1.2, I believe, and 1.2 something in any case. So our value was too high compared to the known value. So they're wanting us to come up with 2 specific errors that would lead to a specific heat that is too high. So I'm going to walk through one example, and we'll see if it leads to the specific heat being too high or not. But I just want to give you kind of a key to how you might do this. So one is, always think about the math that we did. You remember that we first calculated the heat absorbed by the water using our sort of calorimetry table here, and then we calculated this specific heat by plugging everything about aluminum in and solving for that specific heat. And the reason is because what we're going to do is we're going to consider how our proposed change would impact these Q values, and then of course how they'd impact S. So let's start with this. Let's say one of the most common errors that we introduce in calorimetry is that we assume that the calorimeter is going to hold all the heat, but of course some of it leaks out. So let's see what we would think would happen. Well, if some of the heat leaks out, I'm anticipating the change in temperature, in other words, how much the temperature goes up here, would not be as great. So that means that the change in temperature would be slightly smaller for our value. And of course, if that was smaller, then we'd get a smaller heat than we should have. So if this Q is smaller in magnitude, that means that Q is going to be smaller in magnitude. So when it's in our rearranged equation, if we have a smaller magnitude Q here, that means we should have gotten a smaller specific heat than the accepted one. So that idea that heat leaked out of the calorimeter is not going to explain our specific heat value. But you get the idea. So I'm going to leave it to you to try to think of something that could have occurred that would cause us to get a larger heat value, so that we had a larger Q here and would have gotten a larger specific heat. And I'm sure you can come up with something, but you get the idea of how you might solve this.